Video 2 of my P versus NP problems. Recently, there is a website or web page on P versus NP solutions, or I should probably say proposed solutions. I'll link. Just check the video descriptions, and I'll provide a link to the page. Essentially, we'll talk about what the general idea of proofs are, proposed proofs for P equaling NP, and some proposed ideas for P not equaling NP. As I said before, I've done my own research into this thing, and I can honestly pretty much say that if P versus NP is not subject to Gödel's and completeness theorems, I'm pretty sure it's not going to be equal. And here's some reasons why. For the P equaling NP proofs, I found a large number of them are actually finding P algorithms for NP problems, or I should say they're finding more efficient algorithms for one problem. But I mean, it's essentially can be put right here. If there exists even one algorithm that does not, obey those rules, then P is not equal to NP. So they're not really formulating a proof for P equaling NP. They're just simply saying they found a more efficient algorithm for a type of problem, that can happen. It's happened to take the same amount of steps as P as it does in NP. Now, again, they're just finding more efficient algorithms for a certain set of problems, which again is not a constructive. It's not really quite a proof, because there still could exist one that does not obey those rules, and therefore, if one algorithm does not obey the rules, then the set is not equal to each other. Remember, P is supposed to be a subset of NP, believed to be a strict subset, not subset or equal to, because if it was equal to, then P would kind of equal NP. So, anyways, here we have some ideas for P not equaling NP. For example, the factoring problem. Factoring problem is essentially the very efficient argument for against P equaling NP. The reason being is because factoring, as you get larger numbers, it takes more bits to represent the data, and with that, just by default, the numbers get larger. It becomes harder to factor as the numbers increase in size. And so factoring, again, it's not been proven that you can't solve factoring problems efficiently on a classical computer, because you can actually solve it efficiently on a quantum computer. But in a classical sense, factoring primes is believed to be hard to do, and they're very often cited as an argument for P not equaling NP. So just let's say we have a prime that's greater than 1 times 10 to the 73 digits. T will the time taken will be like super exponential. And that obviously would not be an NP. Essentially, P equaling NP can be thought of as can a problem be as easily solved, like a solution found, as it can be verified or checked, such as a subset sum problem. Let's say we have like a collection of integers, like -7, 3, and 4. Find 2 of them and check if they sum to 0. That's finding it. Is the trick, but just checking if two numbers sum to 0 is that can easily be solved in polynomial time. However, finding that actual answer may not quite be in polynomial time, especially if the subset is once the amount gets really large, which is what complexity theory is all about. It's not that the subset sum is usually used to illustrate P versus NP for the beginner. But again, so most likely P does not equal NP. Again, I'll link a bunch of pages. Link the web page that has all these suggested proofs. Recently, there was a guy, I forget his name, who I think in August believed he found a solution to P not equal NP, and I was pretty excited because that's what I thought the answer was. However, mathematicians and computer scientists have been largely disappointed because it's not that there are lots of problems with the proofs and what he's saying. And I looked at it from I kind of briefly overviewed it, and it just didn't seem like like it will be leading to a proof of P not equaling NP. Even though I still believe, and most people believe, that P does not equal NP. Factoring problem, there just seems to be a lot more arguments to say that P does not equal NP. But nonetheless, that should not bias anyone to say that P does not equal NP. For all you know, P could be equal to NP, and then everyone look like a bunch of idiots for thinking otherwise. But anyways, so that's essentially P versus NP. So P equaling NP is just the proofs for it. There's been one paper, I think, that's attempting to define the languages of P, define the languages of NP, using the Turing Machine and really advanced mathematical logic to say that P equals NP. But again, that paper has not been widely completely accepted, and therefore that's not quite a solution. However, most of them just are finding more efficient algorithms for certain types of problems that previously were believed to be intractable or cannot be solved in polynomial time. They were solving something greater. And for p not equal to np, there's a factoring problem, there's a subset sum problem. I mean, there are a lot of arguments again to make that p does not equal np. All right, so this is all for this video. I haven't made one in a while. I'll continue to make my fluid statics video series coming shortly. I've just been not doing too much of that, and then I might do a video series on maybe graph theory or maybe some number theory, maybe something like that. Maybe even cryptography. That's more to come. And that should also start my video series on chess while I'm at it. All right, so yeah, that's all for this video. Hope you guys enjoyed. I'll check out the webpage below if you're interested, and see you guys later.